Hey physics students, this is Scott from PegPrep.com. Welcome to video 1.1 Intro to Kinematics. Distance is the total length of the path an object travels when going from one point to another. Displacement is the difference in position between the object's starting and ending point. For example, consider an object moving on a number line where each unit represents a meter. The object begins at 1, moves to 3, and moves back to -3. To find the total distance the object traveled, you sum up all of the individual lengths of that object's path. When it goes from 1 to 3, it has traveled a length of 2 meters. When it goes from 3 to -3, it has traveled a length of 6 meters. So the total distance is 8 meters. To find the displacement, we have to find where the object's ending point is relative to the starting point. The object's ending point is at -3, which is -4 meters relative to its starting point 1. So the object's displacement is -4 meters. Now let's say that the object began at 0, moved to 3, and then moved back to 0. Here the distance is going to be 3 plus 3, which is 6 meters. But the displacement is going to be 0 because the object's starting and ending points are the same. You can find distance and displacement in 2 dimensions as well. For example, if I travel 3 meters to the east and 4 meters to the north, then the distance traveled is 7 meters, but the displacement is going to be the length of this hypotenuse, 5 meters. Now let's talk about speed and velocity. Speed represents how fast an object is moving. You can find it by dividing distance by time. Velocity also represents how fast an object is moving, but you have to divide displacement by time to find it. For example, if it took me 2 seconds to travel 3 meters east and 4 meters north, then my speed is the distance 7 meters divided by 2 seconds, which is 3.5 meters per second. But my velocity is going to be 5 meters, which is the displacement divided by 2 seconds, getting you 2.5 meters per second. Let's apply this to the number line as well. If it took 2 seconds for an object to go from 1 to 3 to -3 on the number line, then its speed is going to be 8 meters, the distance divided by 2 seconds, which is 4 meters per second, but its velocity is going to be -4 meters, the displacement divided by 2 meters, which is -2 meters per second. One important thing to remember is that distance is always positive, whereas displacement can be negative. Distance is always positive because it's accumulative. For each length of the path the object has taken, you add it to the total distance. So there's no opportunity for it to get negative. But for displacement, it can be negative because it measures the position of the ending point relative to the starting point. So if the ending point is, say, more left relative to the starting point, and if left indicates a negative value in your problem, then the displacement can be negative. There's one more concept to learn before you solve problems yourself. Acceleration. Acceleration is the rate of change in velocity. It is measured in meters per second squared, and it essentially measures how much your velocity changes over an amount of time. So, for example, if an object's velocity increases from 3 meters per second to 5 meters per second in 2 seconds, then the object's acceleration during this time is 5 minus 3 divided by 2, which is 1 meters per second squared. Let's try one more example. If an object's velocity decreases from 8 meters per second to 0 meters per second in 4 seconds, then the object's acceleration during this time is going to be 0 minus 8 divided by 2, which is -4 meters per second squared. Now I want you to apply everything you learned onto these problems. Pause the video and try them yourself. Position, velocity, and acceleration of an object can be represented as a function of time. For example, let's say that x represents position. Then the equation x of t equals to 3t squared plus 4t plus 1 tells you that at t equals to 1 second, the position of the object is 8 meters. At t equals to 2 seconds, the position of the object is 21 meters, and so on. Now, the cool thing is that since velocity is defined as displacement over time, and since displacement is the change in position, velocity is essentially the change in position over time. This means that you can differentiate the position function to get the velocity function. So in the example above, our velocity function is going to be 6t plus 4. And since acceleration is defined as the change in velocity over time, you can differentiate the velocity function to get your acceleration function. So the acceleration function for this object is going to be a of t equals to 6. So this object has a constant acceleration of 6 meters per second squared, regardless of the time. You can go the other way too. Given an acceleration function, you can integrate that to get the velocity function. Then you can integrate that velocity function to get the position function. To illustrate this, let's solve the following problem. I want you to pause the video and read the problem first. Done? Well, how can we approach it? To find the position at t equals to 2 seconds, it would be so great if we had a position function, wouldn't it? Right, so how do we find the position function? We have to integrate a velocity function, but we're not given a velocity function here. So what do? Oh, well, we're given an acceleration function, so we can integrate that to get the velocity function. Then we'll integrate that to get the position function, and then we'll plug in t equals to 2 to get the solution. And that's exactly what we'll do here. Integrating 60 plus 2 gets you 3t squared plus 2t plus c. Since the object's velocity is 2 meters per second at t equals to 0 seconds, we can plug in t equal to 0 into the velocity function and set it equal to 2 to get the value c. Turns out c is equal to 2. So the velocity function is 3t squared plus 2t plus 2. Now integrate this function one more time. This gets us x of t is equal to t cubed plus t squared plus 2t plus c. And since we know the object's position is 3 meters at t equals to 3 seconds, we plug in 3 comma 3 into this function to get the value of c2, which is negative 39. So the position function is t cubed plus t squared plus 2t minus 39, and if we plug in t equals to 2, we get negative 23. That is the final answer. Now let's practice. Pause the video and give this problem a try. If there are functions for position, velocity, and acceleration, can't you graph them out? Yes, you can, and there are important relationships you must analyze from these graphs. First, the slope of the position graph gives you the velocity of that particle at that time. The reason is because differentiating position gets you velocity. So if we have a position graph that looks like this, then at t equals to 2 seconds, since the slope is approximately 2, we know that the object's velocity is 2 meters per second. Second, the slope of the velocity graph gets you the acceleration of the object at that time. This is because differentiating velocity gets you acceleration. Third, the area underneath the velocity curve from time A to B represents the displacement of that object from time A to B, and this is because integrating velocity over an interval gets you the change in position, which is the displacement. For example, let's say we are given this velocity graph for a particle, and we are asked to find the displacement of the particle from t equals to 1 to 3 seconds. To do that, we integrate the velocity from t equals to 1 to 3 seconds, which will have the same result as the area underneath the velocity curve from t equals to 1 to 3 seconds. Since the area is represented by a right triangle, we can just do 1/2 times space time height, which is 1/2 times 2, which gets us 2 meters. So the object's displacement here is going to be 2 meters. In a similar fashion, the acceleration function's integral from time A to time B represents the change in velocity of the object from time A to time B. Let's now solve a problem together. Pause the video, read it first, then listen to my explanation. The acceleration is the slope of the velocity time graph. For the interval 0 to 8 seconds, the velocity falls linearly from 6 meters per second to negative 6 meters per second. So the slope is going to be negative 6 minus 6 divided by 8 minus 0, which is negative 1.5 meters per second squared. You can find the acceleration for 8 to 12 seconds in a similar way. We'll move on to B for now. For B, you need to find the displacement from 0 to 12 seconds, and you can do this by finding the area underneath the velocity curve from 0 to 12 seconds. And to do that, we separate the area into 3 parts, from 0 to 4 seconds, from 4 to 8 seconds, and from 8 to 12 seconds. I just did this to make it easy to calculate the area by using right triangles. If you calculate the area of the right triangles and add the signs accordingly, then you get 12 minus 12 minus 12, which is negative 12, so the displacement is negative 12 meters. If this is the position graph, then the object's velocity is the slope of this graph. The slope is negative 1.5, so the object's velocity at t equals to 4 seconds is negative 1.5 meters per second. Here's the idea behind part D. Since you're given that the object's velocity is 1 meters per second at t equals to 2 seconds, you just need to add the change in velocity from t equals to 2 to 4 seconds onto that original velocity to get the velocity at t equals to 4 seconds. Since this is an acceleration graph now, the area underneath it will represent the change in velocity. Since we're trying to find the change in velocity from 2 to 4 seconds, we have to find the area of this right triangle. That's going to be 1/2 times 2 times 3, which is 3 meters per second. So the final answer is going to be 1, which is the original velocity, plus 3 meters per second, which is the change in velocity, and that gets you 4 meters per second. Now, pause the video and try this problem yourself. Since this is a position time function, the velocity is going to be the slope of this graph. Since the slope is 3 from 0 to 3 seconds, the velocity is then going to be 3 meters per second. And for all the other intervals, we apply the same idea to get the velocities. For part B, a particle is at rest when its velocity is 0, and the velocity is 0 whenever the slope is 0 on the position graph. In other words, whenever you see a flat region. And the flat regions here are from 2 to 4 seconds and 7 to 8 seconds. So those are the intervals at which the particle is at rest. If this is the velocity time graph, then the acceleration is going to be the slope of this graph. Since the slope from 0 to 2 seconds is 3, the acceleration of the particle is 3 meters per second squared here. And you apply the same idea to every other interval. For part D, since this is still the velocity time graph, the displacement from 0 to 8 seconds is going to be the area underneath the curve from 0 to 8 seconds. That's going to be the area of this trapezoid, which is 33. So the answer is 33 meters. There are two more things to cover. First is that speed is the absolute value of velocity in a small interval of time. To understand this, you have to remember why velocity and speed could differ. They could differ because velocity is displacement over time, but speed is distance over time. So if the object goes in a particular direction and then starts backtracking, then while it backtracks, it gets closer to its original position, so velocity decreases. But distance is the sum of all the lengths of the path the object takes, so the distance continues increasing. So these two quantities begin to diverge. Now, let's shrink the time interval for which we calculate the velocity and speed of an object. That is, let's ask for the instantaneous speed and velocity. Over a vanishingly small interval, there's no time for the object to go back and undo its own motion. That is, the motion's effectively one directional over a small instance. So over that instant, if we ignore the direction, then distance and displacement are equal to each other. So the magnitudes of instantaneous speed and velocity will also be equal to. So the only remaining difference between instantaneous speed and velocity is sign. Velocity can carry direction, so it can be negative. But speed can never be negative because distance is always positive. So we can then conclude that instantaneous speed is equal to the absolute value of instantaneous velocity. So when you need to find the graph for an object's speed, you would reflect all of the negative regions of velocity over the x-axis. That is going to be your speed graph. And the area beneath the speed graph over a time interval is then going to be the distance an object travels in that time interval. Now, the second thing to know is when an object speeds up and slows down. When an object's acceleration and velocity are the same, then the object speeds up. For example, if an object has a velocity of 1 meters per second and an acceleration of 1 meters per second squared, then each second the object speed is increasing by 1 meters per second. So 2 meters per second, 3 meters per second, and 4 meters per second, and so on. So it's clear that the speed increases. Now, if the object has a velocity of negative 1 meters per second and an acceleration of negative 1 meters per second squared, then the object's velocity is decreasing each second, but the magnitude of the velocity, that is the absolute value of the velocity, that is the speed of the object, is actually increasing. So the object is still speeding up. When an object's acceleration and velocity have different signs, an object is slowing down. For example, if an object has a velocity of 5 meters per second and its acceleration is negative 1 meters per second squared, then each second, the object's magnitude of velocity, that is the speed, is decreasing by 1 meters per second, so the object is slowing down. If an object has a velocity of negative 5 meters per second and its acceleration is positive 1 meters per second squared, then despite its velocity increasing each second, the magnitude of the velocity, that is the speed, is decreasing each second, so the object is still slowing down. Now pause the video, read this problem, then listen to my explanation. The total distance an object travels is going to be the area underneath the speed graph of the object. Since we're given the velocity graph of the object, we first need to find the speed graph. How do we do that? Well, speed is the absolute value of velocity. So we reflect all of the negative regions of the velocity graph over the x-axis, or the t-axis here. If we do that, the graph looks something like this. And from here, we just need to find the area of these triangles. And if you do, you get 36, so the answer is 36 meters. To know whether the object is speeding up or slowing down at t equals to 6 seconds, you need to know the object's velocity and acceleration at t equals to 6 seconds. If they have the same sign, then the object is speeding up. If they have a different sign, then the object is slowing down. At t equals to 6 seconds, the velocity is negative 3 meters per second, and the slope of the graph at 6 seconds, which is the acceleration, is negative 1.5 meters per second squared. And since the velocity and the acceleration are both then negative, they have the same sign, and therefore the object is speeding up. For the next part, the graph is now an acceleration versus time graph, and because of that, you can find the acceleration of the object at t equals to 6 seconds very easily. It's negative 3 meters per second squared. Now the problem is you need to know the velocity of the object at 6 seconds. How do we find that? Since we're provided that the object's initial velocity is 2 meters per second, we just need to add the change in velocity of this object from 0 to 6 seconds to get the velocity at 6 seconds. And since the change in the velocity is represented by the area underneath the acceleration curve, we just need to find the area of these two triangles and add them together. And that gets you 12 minus 3, which is 9. So the change in velocity is 9 meters per second, and the object's velocity at 6 seconds is going to be 2 plus 9, which is equal to 11 meters per second. Since the acceleration is negative, but the velocity is positive, we know that the object is then slowing down. Try this problem yourself. The process is pretty straightforward, so I won't explain this one. Alright, that's it for our intro to kinematics. As always, practice problems and notes are in penguinprep.com with the link in the description below, and I'll see you in video 1.2.